Good evening, everyone. Welcome to the lecture 7.4 of Power System Stability. In this lecture, we will go through a numerical example to demonstrate the extent of power swing a generator can have, a synchronous generator can have, without losing stability. So the problem goes like this: a synchronous generator capable of developing 500 megawatts power per phase operates at a power angle of 8 degrees. By how much can the input shaft power be increased suddenly without loss of stability? Assume that Pmax will remain constant. See, it is given that the synchronous generator is capable of developing 500 megawatts, which means Pmax is 500 megawatts. Now, initially it operates at a power angle of 8 degrees, which means initial del, which is del naught equals 8 degrees. Now, how much can the input shaft power be increased suddenly without loss of stability? Pmax will remain constant. Now you see the plot. Initially the machine is operating at power angle del naught. At this point we have electrical power output P E naught equals PM naught, because this is a steady state operating point. Now what is P E naught? P E naught equals Pmax sine del naught, right? Pmax sine del naught. But Pmax is 500 megawatts because it is given that the synchronous generator is capable of delivering the maximum power of 500 megawatts. So 500 into sine del naught will give you PE naught. Del naught is 8 degree. It is given in the question. So 500 sine 8 degree will give you PE naught, which is the steady state, initial steady state operating point. So that will give you 69.6 megawatts. 500 sine 8 degrees will give you 69.6 megawatts. Now let del M be the power angle to which the rotor can swing before losing synchronism. If this angle is exceeded, P mechanical will again become greater than P electrical, which means you can see here the mechanical power input PM is increased from PM naught to some PM1. PM1 is at this point. So because of this, suppose there is a swing for the rotor and the rotor swings like this, but the extent of swing goes like this, and if it is beyond this particular point corresponds to the new PM1. That means if PE goes beyond this point, again PE will be less than PM1, or PM1 will be greater than PE, which means the rotor will again accelerate and it will not come back to synchronism. Right. So this should not happen. So we have to find the maximum del M. This is a del M. The corresponding power angle is del M, this one. Now, in the previous lecture 7.3, we had derived this equation 11, which was del 2 minus del naught sine del 1 plus cos del 2 minus cos del naught equals 0. Here also del naught is the initial steady state power angle at which the machine operated. Here del 2 was the extent of swing of rotor. This was not del max, but in this case, in this question, we are asked to find the maximum angle to which the rotor can swing. That means instead of del 2 here it is del M, but this is a variable. This is an unknown here. Del M is an unknown here. Okay. Now del 1 is the angle corresponding to the new mechanical power. That is the changed mechanical power, the increased mechanical power. Okay. Now we use the same equation, but instead of del 2 we substitute del M. Okay. So rotor will again accelerate and synchronism will be lost if PM again exceeds PE. That is, if PE goes after this point, then PM will be greater than PE. Okay, that is what is written here. Now by symmetry, we have pi minus del 1 equals del M, because this angle is pi, right? Pi minus del 1 is this one, this angle. This angle equals this angle by symmetry. So pi minus del 1 equals del M by symmetry. So instead of del M, we are going to substitute pi minus del 1. So in equation 11, we are substituting del M for del 2 And for del m, we are going to substitute pi minus del 1. Okay. So we will have basically two unknowns only, which will be del naught and del 1. Del 2 is not there now. Okay, because del 2 is written as del m and del m is written as pi minus del 1. So two unknowns now. So in this equation we have, when we substitute it, we get del m minus del naught becomes pi minus del 1 minus del naught into sine del 1 plus cos del m has become cos pi minus del 1 minus cos del naught equals 0. Now, after simplification, what we obtain is pi minus del 1 minus del naught into sine del 1 minus cos del 1 minus cos del naught equals 0. So we have two unknowns here, del 1 and del naught, but we have only one equation. So either we have to go for iterative numerical method to solve this particular equation, or we can use trial and error method to find del 1 and del naught. Now del naught we know it is 8 degree, right? So if we substitute 8 degree here, del 1 is the only unknown, but this is a nonlinear equation, right? To solve this nonlinear equation, we have to go for numerical method. Sorry, this is not an equation of two variables. Del naught is known. This is a constant. Okay, so this is equation 13 has only one unknown, but it's a nonlinear equation. Okay, so we have to go for a some numerical method. So by trial and error method, we have found here that del 1 is equal to 50 degree. Now, if what is del m then? Pi minus del 1 is del m. So pi minus 50 will give you del m. Okay, so del m is basically this. In the equation you get here from the plot, you will get this particular point. Okay. Now, what is P electrical? P electrical corresponding to the changed mechanical input, which is PM1. Initially it was operating at P E naught equals PM naught. Now PM naught is changed to PM1. So PM1 at PM1 equals PE1. It will again enter into the steady state operating point, right? So PE1 equals Pmax sine del 1 because the corresponding angle is del 1 here from the plot. Again, I am going to the plot. This is PM1 equals PE1, right? After settling out to this particular power angle, it will be PM1 equals PE1. So the corresponding angle is del 1. So to find that particular electrical power output, we get PE1 equals Pmax sine del 1. Okay, which is equal to 500 sine 50 degree. Del 1 we have found from the equation. Now we get 383.02 megawatts. This is the power. Okay, so this is the changed mechanical power. This one. Changed mechanical power, or the maximum change in mechanical input that is possible so that the machine will not lose its synchronism, because by this change it already reached this point, right? Del m, it already reached del m. If the change in mechanical input is more, if we further increase the if the sudden change in mechanical input is more than this, then it may exceed this point. The electrical power may exceed this point, which means again PM will be greater than PE and the rotor will accelerate and it will lose synchronism. Okay, so that is what happens here. So at the initial operating point, we got that electrical power output was 69.6. Now the changed mechanical power, the new mechanical power is 383.02. So the change in mechanical power, to find the change in mechanical power, we have to subtract 69.6 from 383.02, which will give you 313.42 megawatts per phase. Because in the question it is given, the per phase value is given. Now if you want to find the three phase power, you multiply this with 3. So 3 into 313.42 will give you 940.3 megawatts three phase power. So this is the maximum shaft input, mechanical shaft input in terms of three phase power that can be given to this synchronous machine, which is an initiating disturbance. The maximum initiating disturbance that can be given to this particular machine so that it will not lose synchronism. So that's all with this numerical example. Thank you.